Welcome to ePathshala lecture series on computer science. In this module on data analytics, we will be discussing about various frameworks available for handling big data. So, the objectives of this model are to understand the need for computational problems. Say for example, when we are involving a computational problem, what kind of framework is essential and what type of infrastructure is essential for handling a computational problem is what we are going to learn in today's session. And we will also get to know about the various frameworks which may be used for handling big data. So, to start with, let us first understand a computational problem and its needs. When we take a computational problem, normally it demonstrates few characteristic features. A few to list them are, say a task may be broken into small pieces of work and then it may be handled simultaneously. In other words, it can be handled parallelly. The second important characteristic feature exhibited by any computational problem is execute multiple program instructions at any moment of time. So, we can handle large volume of program at a shorter time span. And finally, we need to solve all these things in less time with multiple computing resources and that can be handled in a very optimal way. So, we require programs broken into simple tasks and we need multiple tasks to be executed at the same point of time and that should happen in a small span of time. So, now when we deal with respect to such kind of problems, what is the need of the hour? So, one important thing that becomes essential is splitting the problem. Instead of running a problem in a linear way, can we split that into subtasks and can the subtask be achieved parallelly or concurrently? Now, why this is essential? Because when we are dealing with a voluminous data environment, we will surely have limitations on the physical hardware components. This limitation will need or will result in, say, splitting a problem and then achieving it parallelly. The second important reason is maybe for economical reasons, because when we go for a more complex task, naturally it will become more expensive. So, instead of working on a very complex task, can we make it simpler subtask and then achieve it simultaneously? The third parameter that will decide why we should go for, say, splitting a problem is performance limit. We may think that when we double the frequency of solving the problem, it may double the performance, but this is not true in many scenarios. So, what is that we need to do is, we need to split, parallelly execute and then merge all the results together for the purpose of achieving a good performance. When we go for very large applications, they naturally demand too much memory as well as too much time for solving. So, therefore, we need to split the applications and then run concurrently. And finally, from a big data perspective, we are of course going to deal with a very large data set and therefore, we require more space. So, these are various reasons why we need to go in for handling the task in a parallel way or in a concurrent way. All these things will result in advantages like increasing the speed and optimizing the resources that is available. And this will be the main objective whenever we are dealing with big data. But what may be a drawback? It may sometimes result in, say, very complex programming models that will make the user to think more, and then when they are trying to implement such an environment, it becomes too complex. So, the need of the hour is take a problem, split it into smaller tasks and then execute it concurrently. Now, in the forthcoming slides, we will see what applications are there, how these applications deal with big data and why such a parallel programming environment or say a concurrent programming environment is essential. So, many commercial applications that are available today, like say your parallel databases and data mining applications, require voluminous data. So, when we are trying to achieve a task by running or executing a data mining algorithm, naturally we need to partition the data, also partition the algorithm and execute parallelly on the partitioned data. Then we have oil exploration problem, wherein different types of geographical parameters are considered for the purpose of exploring oil. Another big task is, say, the task that is executed by many famous search engine giants like Google, Yahoo, etc. In web search applications or in web search environments, what happens is we need to crawl through all the web pages that is available in the World Wide Web environment. since we are dealing with some billions of web pages, naturally we need to execute the task parallelly. Only then we can cover all the web pages that is available in the World Wide Web and accordingly provide recommendations or results which is relevant to the user. And there are many business applications wherein it is web based, we may demand various web services. So such web services, when need to be addressed for various users, naturally we need to do that in a parallel fashion. Other applications like computer aided diagnosis in medicine as well as preventive health care, which is one current hot topic in the big data environment, also requires such kind of parallel computing or programming environment. Then management of national and multinational corporations, management of natural resources, and with respect to graphics and multimedia, when we are dealing with say a virtual reality environment, of course we need to generate or simulate the environment. For simulating an environment, we need to get into various input variables, which is nothing but say the response of an individual to the simulated environment. And when you are rendering, of course you require a very voluminous storage environment, thereby rendering becomes very effective. So in entertainment industry also we require parallel programming. Then when you are dealing with multimedia data like video on demand applications or an application where you involve lot of video streams, there also you require parallel programming. And at last, collaborative working environments in which multiple individuals located in different geographical location can interact on a common topic of interest. So for this also you require data which need to be distributed and services that need to be applied on this data parallelly. Other applications like science computations, digital biology, resource monitoring, exploration and management, space exploration, banks and insurance in which lot of analysis may be done, healthcare and research, retail, automotive production, energy and utilities are few other domains in which we involve voluminous data and we require parallel handling of data so that results may be generated in shorter time span. So for such kind of applications and environments that involve voluminous data as well as that require quicker response, for that we need to know what are the various frameworks that are available. In practical, we are going to deal with open source frameworks only. So what are the various open source frameworks that are available to handle big data? So there are various ways by which you can categorize big data frameworks. One such categorization is provided here. So one way by which you can categorize is, first we can take the frameworks and view it from the perspective of analysis. So now when we normally perform analysis, it may be visualized in the form of tools. So we can first categorize big data frameworks into big data analysis platforms and tools. The second perspective in which we need to visualize big data framework are from the storage perspective. So when we deal with respect to storage, we need to talk about say data warehouses and databases that deal with multidimensional as well as voluminous data. Then big data can be visualized from the perspective of business intelligence. So tools and other software frameworks or interfaces which may be used for performing business intelligent computations. And when we are applying an analysis, of course we will end up with some form of mining. So when we are dealing with data mining, of course we require an algorithm that can scale voluminous data. And the last way by which we can visualize big data frameworks are from the perspective of programming languages. Because when we want to achieve a task, say we need to write an algorithm, and when we are executing that algorithm, we should see to that we have a framework in which we can write and then execute it parallelly. So we can visualize big data framework from the perspective of programming languages. In this module, we will be working towards big data analysis platforms and tools. So one important big data analysis framework is Hadoop, Hadoop Distributed File System, HDFS, MapReduce, GridGrain, High Performance Cluster Computing, Storm, etc., etc. All these frameworks are open source in nature. First, let us start with Hadoop. We will understand what exactly is Hadoop framework, followed by MapReduce, and how these two can together help in achieving tasks from a big data perspective. So what exactly is Hadoop? Hadoop is actually a software platform that makes or allows individual to write and run applications which can work on voluminous data and that too simultaneously. So, whenever I want to handle a data and when I want to execute the task within a shorter time span, of course, I need to divide the data, run the task which may be divided further into subtasks on the partition data and then get the results. This is what Hadoop is trying to support. So, basically it comprises of the following: MapReduce, which is going to be an offline computing engine, and it actually offers the users the way by which you can divide the task into map and reduce tasks and accordingly achieve the entire computation. Hadoop also supports HDFS, which is Hadoop Distributed File System. It supports HBase, which is for online data access, and Yahoo is going to be one of the biggest contributor to Hadoop. When we talk about Hadoop, why Hadoop is very essential for a big data environment? That can be understood only based on the features or specialities of Hadoop. The first important feature that makes Hadoop suitable for big data is scalability. The reason is the number of or the quantum of automated data collecting programs as well as tools are increasing day by day. Therefore, we normally encounter say a very voluminous and scalable storage environment. When we write an algorithm, we must be in a position to scale it to very large data. Hadoop actually supports this feature. So, this becomes the first specialty of Hadoop. Second thing is it is economical. The reason, it actually distributes the data and processes across clusters of commonly available computers, practically in thousands. So, how it makes economical is, see, when you distribute the data, naturally you can run it parallelly, thereby you can make it more economical, and it is efficient. The reason, normally when we distribute the data, we can always achieve the task in parallel or simultaneously. So, we can execute that subtask on nodes where data is located. Thereby, even if one node fails, you still find the data on another node, and hence you can initiate the subtask in the other node. The last but very important parameter is reliable, because it maintains multiple copies of the data, which helps in redeploying the computational task based on say failures. So, what normally will happen when we are executing in a traditional environment is, suppose the data is not available, or if suppose a node fails, then the task need to wait. But here in Hadoop environment, we can always rely, because the data is available in redundant. So, these four features make Hadoop very essential for a big data. Now, let us understand the working principle behind Hadoop. Hadoop actually implements the HDFS, Google MapReduce, using HDFS. In Google MapReduce, what happens is, it actually divides the application into subtasks, or in other words, it divides the application into smaller blocks of works. HDFS creates replicas of the data. In other words, it creates redundant information. The reason behind our replication is, whenever a particular data is not available, then we can still find the data in another environment. That is the reason behind replicas of data blocks. HDFS is actually essential for creating multiple replicas of the same data, and these data are made available in different nodes. Then what MapReduce will do is, the MapReduce will then process the data on the corresponding node where it is available. Practically speaking, when we work with respect to a Hadoop or MapReduce environment, we need to know based on what assumptions these frameworks were developed, and these assumptions are listed down here. The first assumption is hardwares will fail. Yes, of course, in any computational environment, there is lot of chance for a hardware to fail. Therefore, when a hardware fails, the task will get stuck. In order to avoid this, we need to have multiple resources. So, the assumption hardware fails will normally make the entire environment more reliable. The second important assumption is processing will be run in batches, thereby it is happening parallelly. The third important assumption is, whenever we run an application on HDFS environment, what happens is, the size of the data should be substantially large. Only then it is meaningful for running in a Hadoop environment, and the objective behind such a framework is to handle only big data. So, therefore, we assume the data that we are going to use is voluminous in nature, at least in gigabytes to terabytes. The fourth but very important assumption is, whenever we are trying to execute tasks parallelly, naturally it should also have a feature to support some millions of files in a single instance. Only then it is possible to achieve the task in a shorter time span. Then when we are writing an application, applications normally are assumed to write once and then read many times from the given environment. Moving the computation is actually more cheaper than moving the data. The reason is, when we have a data and when the data is required say in another environment, shipping of data becomes very difficult because of various reasons like security and other database anomalies like inconsistencies. So what must be taken care of is, instead of shipping the data, is there a chance for shipping the algorithm or the computation. So shipping the computation becomes more cheaper when compared with shipping of data. And the last assumption is portability is treated to be a very important assumption. Based on these assumptions only, Hadoop framework has been designed, and these assumptions actually make the user to understand what exactly Hadoop framework is really for. Now why should we use Hadoop? Say for example, we are in the process of handling say 20 terabytes of data. Say we have a data set, assume its size is 20 terabytes. If you are going to handle it say in a single node at the scan rate of say 50 megabytes per second, it will take approximately 4.6 days to process the 20 terabytes of data. But if I am going to handle it say in 100 node cluster, that is a cluster comprising of say 1000 nodes, then with the same scanning rate it will be achieved in say just 6.6 minutes. Now this is a point where people must understand, we need to do the things parallelly and we need to achieve the final outcome in a very shorter time span. And when we want to execute certain things in a shorter time span, we actually keep in mind that we are dealing with a very large data. So when we are trying to handle a very large or voluminous data, then there is a need for Hadoop environment. So Hadoop, when it wants to be efficient, reliable and usable, it must contain the Google file system, famously called as GFS, and then the Google's MapReduce. In the forthcoming slide, we will discuss about what is Hadoop distributed file system and how MapReduce helps in achieving this task. Hadoop distributed file system is actually based on the Google file system. Here what it does, it takes a data and then it splits the data into large blocks and distributes it across node. Normally when it is distributing, it should also replicate. So when it is replicating, we can replicate it to the maximum of say 3, that is we can handle 3 replicas. Among the 3 replicas, 2 may be handled in the same rack and 1 may be handled say in a separate node. Why we should handle 2 partitions in the same node is, even if one particular data fails or say one part of the hardware fails, we can still find the data in the same rack. Thereby networking issues can be solved or shipping of data can be stopped. If in certain scenarios, if the entire rack, all the machines or nodes in the entire rack fails, then only we need to look in for the data in another node. And all these data cannot be directly mounted onto an existing operating system. So what happens is, when we are trying to work with respect to Hadoop environment, this replication and distribution makes it highly fault tolerant, and this will always result in low cost hardware. And when we are having the data always made available, naturally you will have a high throughput and we can always have an access to the data at any point of time. And it also relaxes certain POSIX requirements which are associated to enabling streaming of information. Now this Hadoop, how exactly it works, what is the fundamental architecture behind it? In Hadoop environment, we actually deal with a master slave kind of architecture. The master is actually called as say the name node and the slaves are called as data nodes. What exactly happens is, when a particular client issues a program or say issues a task, it will be assigned to say job trackers. The job trackers in turn will look in for task trackers that actually will take the task and then execute the task in the respective machines or nodes. So a name node has to keep track of how many task trackers are there, and the task tracker in turn will execute the task. Now there is one important thing to be noted here is, suppose if a task tracker fails, there is a chance that part of the task may be re-executed. But when a job tracker actually fails, then the entire task need to be rescheduled. So we need to be very careful on the job tracker when compared with task trackers. So, this architecture when diagrammatically represented will look like this. So, you will have a client, the client will submit job to the name node, the name node in turn has to identify job tracker and assign the task to job tracker. The job tracker in turn has to identify task trackers. The task tracker will know what are the nodes in which the data is available, the required data is available. Accordingly, it will execute the task in the respective data nodes. Here from this diagram you can find data replication. So, you may see one data being replicated in 2 or more nodes, and 2 of the replication will be available in the same node and 1 may be available in another node. So, here this diagram will give you a clear picture of how the job tracker and the task tracker are executing. So, the client submits a job to the job tracker, the name node will take care of the job tracker as well as the task tracker. The job tracker in turn will identify what are the nodes in which the data is available, and accordingly it will assign the task to the task tracker. The task tracker in turn will fetch the data and then execute the corresponding task. This is the functionality of Hadoop distributed file system. Now, how a MapReduce will help in achieving this parallel tasking? For that, first we should understand what is a MapReduce. MapReduce is a programming model which Google has used for successfully implementing its big data and computation on big data sets. So, what exactly this MapReduce will do is, when a user specifies a computation, it will be specified in the terms of map and reduce functions. Now, these maps and reduce function will be automatically parallelizing the environment. So, what must happen is, we need to take what are the nodes that are available, where are the data is available, accordingly things need to be scheduled. So, fundamentally any hardware failure or machine failure or in case of any inefficient communications, everything need to be handled on the fly and automatically. So, MapReduce will take care of all such performance issues. Now, how a MapReduce will work? So, this can be seen from this data flow diagram. A user job is fundamentally broken into 2 tasks, one is the map task, another one is a reduce task. The data is nothing but a sequence of key and values. Now, what the map task has to do is, the map task has to take the key, the corresponding value, and identify an intermediate output key and its respective values. Once the intermediate keys and values are identified, the task of reduced job is to use the keys, in other words to read the respective key and value pairs, do the computation, merge the result and then give out as a persistent data. This is how a MapReduce environment will work. The same we can visualize using this execution diagram. A user actually invokes say a master. The master will in turn invoke many workers. Of these workers, few workers will be map and few workers will work on the reduce. Now, what the map function has to do is, that is the workers that are assigned the map task has to identify from the input file where the respective data is available. Now, it will have a key and a value. With this key and value, it has to identify where exactly, in other words in which particular block the data is available, and the value that is available in the block will be considered as my value. So, now the worker, which is nothing but the map task, need to take a key and value pair, identify from the input file the intermediate key and corresponding value pairs. Now, these intermediate key and value pairs will be written into intermediate files, which is going to be local, in other words local disks. Now, the task of map function is finished. Next, what we need to do is, the reduce functions need to be invoked. The reduce function will now look into the respective local disks, read the intermediate key value pairs, execute the task, sort them, merge them together and then provide us one single output file. Normally, every reduce will end up with individual output files, and at last all these output files need to be merged together and presented as one single output. This is how a MapReduce executes. Now, let us take a sample scenario, and from this scenario we can understand how running a job on Hadoop environment may be visualized. Assume you have large or huge text documents. Here for explanation sake, we have taken say a statement and we call that to be a huge text file. So, this text file contains the text hi, how are you, and the other text file contains hello, hello, how are you. Now, what is that we need to do is, we need to split this job into two, one is a map task, another one is a reduce task. So, what we can think of is, maybe we can think as say counting the frequency of the terms available in the huge file as say map task, and then merging these intermediate frequency values together to generate the final output may be considered as the reduce task. Now, when you take a look at this diagram, you will be in a position to appreciate how a map and reduce task may be easily visualized from this given scenario. So, for this given scenario, the text hi, how are you is taken. Now, this is going to be the value and the map function will identify in which particular block it is available. So, it will take the corresponding key and the value. Now, this key and value will generate another set of key and values. So, here the key values are the keyword actually that is part of this text file and the corresponding frequency. Similarly, for the second input also, an intermediate set of keys and the corresponding values, which is nothing but the frequency of these values are generated. Now, the map task is over. All these intermediate key values will be returned into the local disk. Now, the reduce functions need to be invoked. So, the workers which are assigned to reduce functions will now read from the local disks and then identify how many number of times say the keyword R has occurred in all these intermediate environment. So, now it is available say one number of time from this intermediate environment, and from this environment it is available the second time. So, therefore, the R keyword will now be associated to two occurrence. The reduce task has to merge the results. So, the R keyword when merged with the respective frequency value will provide a frequency count of 2. Likewise, for hello, hi, how and you, for these keywords also the reduce task need to compute the accumulative or cumulative values, and then the merged information will be saved into the output file. So, here the task of computing the frequency of keywords available in large text files are divided into map function and reduce function, where the map function takes the data from the storage, does a computation which is nothing but counting the frequency. The reduce function will take the intermediate results from the local disk, merge the results together and then generate a single output. So, this is how we can understand how a map reduce function works. So, in summary, we were discussing about parallel processing environment. In parallel processing environment, what exactly happens is, we are actually taking a task, we are splitting the task and then we are trying to execute the task in multiple environment. For that you require data that is available in a distributed fashion. So, we need to take the task, divide it, and when we want to execute it, we require the data in duplicate. And when we are dealing with respect to a big data framework, what happens is the same may be visualized by means of frameworks like Hadoop, Hadoop distributed file system and then MapReduce. In Hadoop, we discussed about its architecture, its characteristic features and when it need to be used. With respect to Hadoop distributed file system, we discussed about what is the usage of Hadoop distributed file system in terms of distributing the data and then handling the data whenever it is not available say one node or in one framework. And finally, the MapReduce provides the user say a programming framework wherein user can define task in the form of map and reduce function, which may be used for further executing the task on voluminous data which has been partitioned, execute the task, fetch the intermediate results, merge and then provide the results in a uniform way. So, this is how Hadoop, HDFS and MapReduce together will help in achieving various computational tasks for a big data perspective. Thank you.